Welcome to Moneyball Boston Red Sox. This is video 1 in a two-part series that aims to integrate optimization and machine learning models with interactive user dashboards. This video focuses on identifying organizational use cases for bridging the gap between traditional business intelligence reporting and data science. More importantly, this video will demonstrate how powerful of a tool Tableau is when connected to external clients such as R, Python, or MATLAB, and how developers and end users can benefit from this integration. In part 1, we'll focus specifically on the Boston Red Sox and how advanced analytics can help determine player selection based on the number of team, player, and position constraints as teams prepare for the start of the 2020 season. Part 2 will focus on the underlying calculations and how to create optimization models within Tableau using a local R server. So let's take a look at the dashboard and explore a number of features that it has to offer. Now, since this dashboard is running in real time against an R server, we'll just go ahead and confirm that our connection is running as expected. We'll take a look at a few of the objective statements that the user has to select from, and you can view an objective statement as a cost function where you're trying to minimize costs or maximize efficiency. And the purpose of optimization modeling is to maximize your objective statement or minimize your objective statement. So in the case of the Boston Red Sox, the user can select to maximize the overall team value, offense, defense, batting average, on-base percentage, home run projections, and bargain. Overall value is a score that is given to each player in Major League Baseball based on how well that player is likely to perform on the Boston Red Sox. Looking at 10 years of MLB data and using advanced machine learning models, we were able to determine which player statistics would lead to a player's success on the Red Sox. An example would be at what height is a home run hitter's ball when it crosses 310 feet in left field. If it's not above 37 feet, then it is not a home run, or how well a pitcher has performed against other teams in the AL East in sub-40-degree weather. It acts as a single score that is based on 50 metrics that allows us to compare each player and their likelihood of success on the Red Sox. We'll take a look at a specific example in which the Red Sox are looking to maximize their overall offense. So from the objective statement, we'll select maximize offense, and we'll enable trading within all teams. And we can see in the center under the Fenway scoreboard, we have two teams, one that's optimized and one that's Boston. The optimized is showing us the results from our constraints that we're feeding through to the optimization model, whereas the Boston score reflects the score of the players on the current Boston Red Sox after being assessed by our model. In this example, we're going to enter the same constraints as the current Boston Red Sox to see if our optimization model will yield a higher offense score than the current Boston Red Sox. To make bulk updates to constraints, we can navigate to the Constraints tab, which will prevent the model from rerunning each time we update a constraint within the parameters. As we can see from the Constraints tab, we have a number of constraints that weren't previously available on the main dashboard, and these constraints are broken out based on team constraints, player constraints, and position constraints. Here we can enter the same team size as the current Boston Red Sox, equal to 21, and we can enter the current team salary of the Boston Red Sox, which is approximately $116 million. Next, we'll take a look at the statement constraints, and this is only accessible on the Constraints tab, so the user can select that the constraint is less than the value that they entered, equal to the value that they entered, or greater than the value that they entered. Under player constraints, we can have the model run against only players that are potentially available, or all players within Major League Baseball. In this case, we're going to run it against all players within Major League Baseball to give us our most optimized lineup. We'll now change position constraints as well to reflect the current Boston Red Sox. In this example, we're going to set both our first baseman and shortstop greater than or equal to 1. By clicking back, we will be navigated back to the original dashboard, which will execute the model. We can see here that the model is currently assessing each position to determine which player meets the model constraints, as well as which player should be a starter, which are those players indicated on the field. Looking at the scoreboard, we can see that the offensive score of the optimized team has a score of 70.7, which is higher than that of the current Boston Red Sox at 47.4. In fact, when looking across all relevant metrics, we can see that the optimized team performs just as well, if not better, than the current Boston Red Sox. And this raises the question of, can we reduce the payroll for 2020 and still return back a team that has a similar, if not higher, offensive score than the current Red Sox? So in this example, we're going to reduce the payroll for 2020 to $80 million. And we're going to look to see which players are returned back by the optimization models and how this affects the overall team score. And what we can see is that by reducing our payroll by roughly $30 million, we've only had a reduction in our offense score by roughly 1 point. So a very small reduction given the large reduction in salary. When looking at the players that the model returned, we can see that Rafael Devers, a current Boston Red Sox player, was returned back by the model as being the most optimized player to play in that position, which is great because he's currently on the Red Sox, but that means we don't necessarily have to trade for a third baseman, and we can possibly use players in other positions. So we'll go ahead and update the constraint for third base to equals 0, so the model should not return back a third baseman. Instead, it's to look to maximize the offense score across all other positions. So it's going to rebalance the entire team, possibly selecting different players that maximize the overall offensive score. And then, of course, it's going to return back the starters and the bench players and pitchers as well. Another helpful feature is that by hovering over any player that's been proposed by the model, we can see additional statistics on that player in relationship to the current player that plays in that position on the Boston Red Sox. So we can compare the optimized selected player to the player that's currently playing in that position, and we can make the decision if we want to retain that player or if we want to have the model generate a new player in return. By selecting a player, we can also see additional statistics on that player. So we can go ahead on the bottom right and look at all their past seasons that they have in Major League Baseball. We can also take a look at how they're currently trending within spring training. And again, these are metrics that are used in the model to determine the player's overall value, their offensive score, as well as their defensive score. Now, Willson Contreras is a highly sought-after player, and after a few hours of generating this model output, we learned that he's been traded to another team, and we therefore want to exclude Willson Contreras as a potential catcher. So by clicking on Willson, we can then say exclude player from output, which will rerun the model to optimize the team's overall offense score by selecting new players. And in this case, it's just going to select a new catcher. And we can see that Kyle Ryan has been selected, and the overall offense score has remained unchanged at 69. Now, when looking at the scoreboard, although the offensive score of the optimized team is higher than that of the current Boston Red Sox, we can see that the overall value score is lower than that of the Red Sox. And remembering back to the overall value score, which is computed at a player level, and it determines how well that player is likely to fit into the organization and playing for the Red Sox at Fenway, we believe that by maximizing the overall value, we may have a more well-rounded team than to just maximize the offensive score. So we want the ability to do comparisons and compare how maximizing the overall value would compare to maximizing the offense given the current constraints. So we're going to navigate over to the comparison view, which allows us to run multiple scenarios given two team constraints. So team 1 is defined by the output of the blue constraints, team 2 is the output of the gray constraints. And we're going to update Team 2 to reflect the Yankees, in this case, with their $230 million 2020 payroll. Currently, they are at a team size of 26 players, and we can update their individual position constraints below to 25 constraints. Then the model essentially will select a player that fits into any position that maximizes their overall value. Now for Team 1, we're going to set this equal to the current Red Sox constraints. So again, we'll leave maximizing overall offense, but we will update the team salary to $116 million, and we'll keep the team size as of right now at 21 players. And when looking at the scoreboard, we can see that although we have maximized our overall offense and it's higher than that of Team 2 and the Boston Red Sox, our overall value is relatively low at 64. So let's rerun the model to maximize overall value while keeping all the same constraints the same. And we can see that overall value is maximized at roughly $112 million. We can get an overall value of 88 across 21 players and with our position constraints. And we can see each of the overall value scores of every player that's been selected, as well as their salary constraints. Now, we believe that by paying more, we're not necessarily getting more. We want to test this theory by entering a 2020 salary cap that's significantly lower than what we intend to spend, so roughly $75 million. And we can see here that the overall value of Team 1 has remained relatively unchanged. In fact, every single measure that's relevant is either on par, if not better, than Team 2 and the current Boston Red Sox. So this certainly raises the question of, can we actually spend less and get more in return, which is the theory of Moneyball in itself and how it originated. So we want to look to actually maximize our bargain, and bargain is a calculation that looks at each player's overall value in comparison to the salary that they're demanding. And we want to see if by maximizing our bargain, if this actually gives us a higher, well-rounded team across every metric. So by looking at the overall score when maximizing our bargain, we get a score of 80, which is significantly higher than the current Boston Red Sox. Now, keep in mind, we only have to pay $12 million to get this score of 80, and our bargain score is significantly higher, offensive score is significantly higher, and every other category is actually higher than that of the current Boston Red Sox. Now, we're going to update our parameters to reflect that of the current Yankees, while keeping our salary remained unchanged. So we're going to keep the salary at $75 million, but we're going to update the team size to 26 players, and we're going to update each of the individual position constraints to match that of the Yankees. And we're going to look to see if we can get a team that's on par with the Yankees on paper without having to spend as much. And when we look at the model output in itself, we can see that it's very much in line with what the Yankees are getting by spending significantly more. In fact, for spending $15 million, we get a team that is only 8 points off of overall value than that of a team that is spending $228 million. And we're very much in line with every other metric that is relevant to evaluating the team's performance. So we're going to click back, and we're going to have the model show us exactly which players were returned back and who would be our starters and our bench players and pitchers based on each of the constraints. And we can see when looking at the scoreboard that our optimized team on paper is significantly better in every category than the current Boston Red Sox. In fact, we have more players and we're $100 million less than the current Red Sox. And this is exactly what Moneyball aims to prove, that small cap teams can find undervalued players by introducing their own statistics and analytics to find players that fit their needs better than just going out and paying these large sums for players that have overglorified statistics. It's really about finding players that fit your lineup, your organizational structure, your field dynamics, and the way that you plan to run the club there. Lastly, we'll take a look at another example in which optimization models may be helpful in this scenario. Let's say midway through the season, our team is struggling to bring in runs, so our RBIs are dropping, but our home runs are increasing, and we think this is a result of our on-base percentage declining. So we want to maximize our on-base percentage, and we're willing to make an immediate trade to do so. Of course, we don't want to trade with the Yankees because we're not sure how the postseason is going to shape up. And we only want to bring on 4 additional players. And again, because we're playing Moneyball, we don't want to spend much for these players. We only want to spend $18 million maximum. Of course, we're happy if we can get more for less. And we want to look at only players that are potentially available. So we've calculated the probability of a player saying yes to an offer, and each player has a probability associated with them, and we only want to run this model against those players. And so we're going to update our batter constraints, and we're essentially going to zero out all of our position constraints. And this is essentially allowing the model to return back the 4 best players regardless of their existing position. And so we're going to rerun the model. And we can see here the model is going through each position to determine the 4 best players that will maximize our on-base percentage. And we can see here that it returned back 2 right fielders, and it selected the best right fielder to be on the field, but it essentially brought back a bench player, and we don't want a bench player right now. We want to bring back players that we can put immediately to use. And if we have 2 right fielders, only one will get placed to use. So we're going to go back to constraints, and we're going to say that right fielder has to be less than or equal to 1. So essentially don't return back more than 1 right fielder. And again, the model is going to recompute who should be out there in order to maximize our on-base percentage. And we can see that these 4 players that the model has selected have a on-base percentage of 34% compared to the current Boston Red Sox that have an on-base percentage of 21%. So they would be ideal players to introduce into this lineup if the focus is going to be on increasing the on-base percentage. And again, we were able to do so for significantly less than we had originally expected of $18 million. We were able to bring on these 4 players for less than $6 million. So this is the idea of Moneyball. It's to allow small cap teams the ability to play against teams like the Red Sox, teams like the Yankees, who have these very high salary caps and essentially can afford to pay for top tier talent. This really gives a team that focuses on analytics and optimization and simulation the ability to select players that make the most sense based on their team structure, based on their park, based on their management constraints. Now, although this example focused on the Boston Red Sox and Moneyball, scenarios just like this are very relevant in business. In fact, we see them on quite a regular basis where clients are trying to introduce similar optimization models, whether it's because an initiative just received funding and they now need to staff an initiative with resources, and they must determine how many managers, how many data scientists, how many analysts with different skill sets across different applications and domain knowledge need to be staffed on the project to maximize the project's overall success rate. So anytime there's a resourcing question that has a number of constraints, optimization models are very powerful in creating these very dynamic dashboards that use the integration that Tableau has with R and external clients, makes them that much more powerful in the hands of a true BI developer at the intersection of data science.